look at
So
the.
they don't fly if you have something to do with it, unless it's something serious.
Yeah, that's kind of the same here, I think.
Seriously?
But I mean, it's different, you know.
Yeah.
You're in America, you don't want to do anything like that.
Okay.
FBI will break down your door.
Oh yeah.
But yeah, there's not really an FBI here, so as long as it's not going to damage anyone, it's probably
Pay the
okay.
maintenance fund?
Oh yes, and I'm not allowed back.
Oh, really? What have you done
No,
there?
I'm just joking. All right, specific heat capacity next.
Oh, so you,
You know this one?
yeah. What's that? Heat.
Specific heat capacity.
Oh, sure.
Yeah. Got it? Yeah.
Yes, please.
Right. Uh, so we have a couple of things to look at. So to get you thinking now, why does metal feel colder than plastic? So imagine we have a piece of metal at 10 Celsius
Uh-huh.
and a piece of plastic at 10 Celsius. Which will feel hotter or colder? Well, they should feel the same, you would think.
Yeah.
But no,
But the metal feels colder.
yeah.
And another thing, why does water at 10 Celsius feel colder than air at 1 Celsius? I mean, if you were in a bath at 10 Celsius, you will definitely feel cold.
Yeah.
But if you were outside and the temperature outside is 1 Celsius, although you'll be cold, you'll be okay. It wouldn't feel as cold as being in the water.
Because we are wearing clothes.
No, no. Well, go into the bath with clothes on with 10 Celsius, it'll still feel cold.
Because
So, clearly temperature is not enough by itself to describe heat, yeah?
because the area is the larger in this way.
Not to do with the area, not really. We need another way to talk about heat and temperature. Metals will feel hotter sooner than plastic. So, if you had a piece of metal on a heat source and a piece of plastic on the same heat source, the metal will get hotter quicker than the plastic.
Mm-hmm.
You know this, like if you have some metal near a heat source, it will feel hot very quick.
Yes.
Like
Yeah.
sometimes here in Ireland, like the temperature is 13 or 14, but the wind is like very cold.
Yes,
Yeah,
yes,
it's look like 5, 6,
yes.
less than.
In fact, what's happening is conductors will get hotter than plastics. Um, Basically, some materials warm up faster than others. And why is this? Well, different materials have different capabilities when it comes to absorbing heat. So if I pump heat energy into something, the material won't take the heat energy at the same rate as the other materials. So for example, if I try to put heat into my coffee, the coffee will warm up faster than if I try to put it into wood. Yeah. So different materials have a different capability of increasing their temperature with absorbing heat.
Can you collect like this heat energy with not in any substance?
No, it needs to be because heat
In
is
a medium.
yeah, it needs a medium because heat is really just kinetic energy of molecules. So there must be a medium, usually water, but it must be something.
You can say what some
Air, water, whatever, but there must be some mass.
and you can freeze the temperature, like you can keep it like only minus something or minus something.
Yeah, yeah, you can hold temperatures. That's called a heat bath. Um, so we have this notion now called specific heat capacity of a material. It's the amount of energy required to raise 1 unit mass of it by a unit of temperature. So I'll show you what that means. Imagine here I have 1 kilogram of water, and I would like to increase its temperature by 1 Kelvin or 1 Celsius. I would need to put in about 4,200 joules of heat energy. This number here is called the heat capacity. It's how much energy you require to increase 1 unit mass of the material by 1 unit of temperature. And it's different for each material. So for water, you need 4,200 joules of energy to increase a kilogram by 1 Kelvin. Sometimes people use grams. So for water, if you have 1 gram of water and you want to increase it by 1 Celsius, for example, you would need 4.2 joules of energy.
So do we have to remember all
No. Yes. So what are the units here? Well, the units would be, if you look here, it's joules per kilogram per Kelvin. Or if you're using grams and Celsius, for example, it'll be joules per gram per Celsius.
How could they ask? Then what could be the percentage?
No, I'm just showing you the units. So here for the water, I would say the heat capacity is 4,200 joules per kilogram per Kelvin.
Oh, but we know
For
that.
water.
Yeah. For water. Okay, so please make note of the definition. It's sometimes asked in the exam. I prefer to say unit mass, but if you prefer, you can say 1 kilogram of mass.
Units mass. No, there's definition for heat capacity, then there's definition for specific heat capacity.
No, it's really specific heat capacity, but I notice most books nowadays are just calling it heat capacity. But
No, like they're different, kind of.
if there is a difference, we don't need to know it for the exam. Mhm. Got that? Okay. So, the energy delta Q required, now you don't need to write all this down, maybe just a formula, but if you ask yourself, how much energy do I need if I want to increase the mass of a material by a particular temperature amount? So for example, my question could be, how much energy to increase 2 kilograms of water by 10 degrees? The formula is this, Q equals mc delta theta. So let me explain each part. This is the energy you need in joules. This is the mass of the material in kilograms. This is the heat capacity in joules per kilogram Kelvin. And this is the change in temperature, the increase in temperature you would like.
That's the mass.
Is that now?
At least the formula, but whatever. You
That's
prefer.
a Q equal?
Delta Q equals
Yeah?
Mm.
Okay. So, for a simple example, if I want to increase 1 kilogram by 1 degree, this formula says the amount of energy I need is how much?
1 m.
Now, 1 kilogram by 1 degree.
MC. Sorry. C, sorry.
C, yes. Which is specific heat capacity. So, if I want to increase water by 1 degree and I have a kilogram of water, I would need 4,200 joules. So it's important to know that different materials have different heat capacities. Here's a table of some materials. So for example, Liquid water needs about 4,200. Now you need to write these down because the questions will need the values. KJ, are you writing this down?
My pen is broken.
That won't be the only thing broken if you don't write this down.
Funny man.
What is this one?
Oh no. Wonder no.
Okay.
Next one.
So there's solid water.
Yes, also known as ice. Which so in fact ice is easier to increase its temperature. You per kilogram of ice you require 2,000 joules to increase its temperature by 1 degree. What is the other one I'm going to look at next?
Yeah?
No.
Yes?
Yes.
Gaseous water,
Yes.
also known as steam. And again, that only needs about 2,000 joules per kilogram per Kelvin.
2000 is known as 2080.
What's gaseous water?
Steam.
Oh.
I believe this is the adjective for gas.
Yeah.
Then copper.
Copper is tiny. It's very easy to increase the temperature of copper. You need only 385 joules per kilogram to increase the temperature by 1 degree.
Gold.
Next is milk.
What is
I just put that in for a laugh. Milk is 2,850.
That's so big cookie.
Yeah. So I mean, this is interesting because it means, think about it. If you have a pot of a pot of cold water and a pot of milk, and they're both at the same temperature, and you want to increase the temperature by 1 degree, you need to give the water twice as much energy as the milk to make that 1 degree increase. So that means if the heat source is the same, which will get hotter quicker?
milk?
The milk. How much quicker? In fact, you can say it's twice, well, no, it's not quite twice, because it's more than 2,000, but it is a good bit faster than water. So this is why if you're cooking with water and milk, the milk will reach its temperature sooner than the water, because it requires less energy for each degree increase in temperature.
Okay.
Yeah. Alcohol is near 2,000.
Near 2000.
Yeah, 2,300.
Okay. No.
Lead is tiny. It's only 129, meaning that to increase the temperature of lead is extremely easy to do. At 129 joules, it will so easily get hot.
Economical.
Yes, which is one of the questions we'll have.
Yes.
Air is actually surprisingly high. You would have thought air would be quite low, but it's still in the thousands. You require 1,000 joules to heat up a kilogram of air by 1 degree.
So the sun cannot heat up the air in Ireland.
Yeah, our heat capacity is higher. It requires more energy to heat up the air. Okay. Why do materials have different heat capacities? It's complicated. It's very, very complicated. We'll have a simple explanation later, but of course it's at the end of the course. But the simple explanation will be a poor explanation. The reason is quite complicated, so it's complicated.
They are made of different things.
Yeah, but how does the structure of the atom affect its heat capacity? You know, it's complicated. It's not simple. It's not like, oh, big atoms have big heat capacity and small atoms have small heat capacity. It's complicated.
Maybe the bonding between them.
Could be bonding, it could be structure, could be how free they are, it could, there's
You know,
many
if the
things.
bonds are strong, like closed enough, you require more
Yeah, but you
energy
don't
to
care
build.
about the bonds between the atoms so much. It's how free they could move, So you don't care about how strong the hydrogen and oxygen bonds are in H2O. Because heat is kinetic energy, you only care about how fast the molecule can move. So the bonds might not even be important for the heat capacity. So like I said, it's complicated. Let's have a look at some questions. So, how long would it take to boil a kettle, to boil water to make tea? So let's do this one here. Right, so we'll pick up the numbers ourselves. So firstly, you get some water from the kitchen. What temperature would the water be at?
Room temperature,
From the tap.
no,
No way.
15,
Have you turned on taps here in Ireland? The water does not come out at 20.
10 to 15.
Hot water comes out at like 20.
Don't
Yeah, but
use
you don't
power.
use. Yeah. We're making tea. You should use the cold tap. Use the hot tap for drinking. You shouldn't do this now.
Why?
No,
Huh?
Why?
It's not as fresh as the cold tap.
yeah.
Did you know this? Well, you know it now. Don't worry. You won't be sick for much longer. 10 Celsius. Now, what is the desired temperature? What temperature do you want the water to be at?
100.
80.
Yeah. Well, you'd like to get it to 100 to make tea. How much water would you need? So what's the mass here?
250, 350.
Something like this. So we'll say 0.25 kilograms of water. Yep. So what's the change in the temperature? It's 90. 90 degrees increase. The heat capacity of water is 4,200 from the table. Well, 4,180 or something.
Okay.
So how much energy do you need? You need mc delta theta, which will be 0.25, 90, 4,200. Now what's that?
The mass.
Yeah, what's the total here? Look, do it with calculator.
If you brought it, use it. Calculator at least someday.
Yeah, actually, you have it.
94,500.
You need 94,500 joules.
Yeah.
Now, how long will this take? So, how are we heating the water? We're using an electric kettle. Okay? So, the power of the electric kettle is 2 kilowatts, 2,000, let's say. Yeah, that's usually.
One.
No, 2 kilowatts, 2,000 watts.
One was the question.
Huh?
Okay.
How long it takes?
How long it takes? So, we need to know how quick.
But it was 1 kilowatt in question.
Oh, what? Oh, oh yeah, I was making up one. Yeah, so we use a small travel kettle then. Okay. So the power is 1,000 watts. But what's the formula for power? Work over time equals power. So time equals work over power. So how much work do we want to do? Well, we want to do 94,500 joules of work. This is how much energy, heat energy, we want to pump into the water. And what's the power? It's 1,000. So it should take about 95 seconds.
Approximately 1 minute and
1.5 minutes. Now that's 250 grams of water is a very small amount. It would only be 1 cup of water. So 90 seconds does seem like about the right time to take the heat up only this. Yeah. Yeah. Yeah, try it. Now, you have to check what the power of the kettle is. It will say it on the bottom or something. Okay, have you got that? Yeah. Alright. Right, a 100 gram block of ice goes from -10 to -1. How much energy was required to do this? So for this one here, you've got your block of ice. What's the temperature at the beginning? -10. And the temperature at the end? -1. So what was the change in temperature? 9. What is the mass? 0.1. That's what it said. And what's the heat capacity of ice?
1,000.
2,000.
Ice,
2110.
So, the amount of energy that the ice block received from the sun, because the sun is given it heat energy. So the sun is given it heat energy.
Okay.
So how much heat energy does the ice block get? It would be mc delta theta, which is 0.1 times 2110 times 9. So, what's that now?
About per hour.
Yeah?
1899.
Joules.
You sure, bro?
And we can find the time too.
Check it.
Seems legit. No, we can't find the time because we don't know the power.
Of the sun.
Yes. Yeah. Okay. Next, go on, yeah?
Yeah.
No, I'm sorry. Continue?
Yes, please.
Yeah.
But you can, do this practical,
Oh, sorry.
do this practical in somewhere of
Yeah, you
open
could do it,
area,
right?
and we can check that at that temperature, at that atmosphere, what was the heat energy.
Yeah, I mean, these are things you could work out. Yeah, just need a good thermometer. That's all. Okay. Now, here's one. I'll explain it. What you've got here is a room which is 10 by 10 by 5, and an electric heater is heating the room. So, let me draw it. What did I say? 10 by 5 by 5. So you've got a room which is 10 meters this way, 5 meters this way, and then 5 meters high, we'll say. It's a room. Now, the temperature of the air is 10 Celsius. That's pretty cold. You would like to increase the temperature to 20 Celsius. You are using an electric heater.
Steve.
Yep.
10.
Oh, sorry, it's a 10 by
And
10 by 10 by 5. Yeah, okay. Well, it's my question, so I can change it if I want. Right, and you're using an electric heater in the room that's giving in heat energy to the room to heat it up. So, how much heat energy, and therefore how long will it take to reach the temperature? Let's calculate it. So, what is the change in temperature? 10. Yeah?
Okay.
yeah.
What is the heat capacity of air? It's like 1,000 and something? 80?
1012.
We'll just say 1,000. Oh no, we'll do it properly. 1,012. What else do I need to know? That's delta theta, not delta Q.
Yeah.
And we want to calculate the delta Q. The mass. No, do we have the mass?
No.
No, but we know density is mass over volume, so mass is density multiplied by volume. What's the density of air? Do we remember?
Yes.
It's about 1. It's like 1.4 or something. So in this question,
1.3.
I said take it to be about 1. So we'll take it to be about 1. Yeah, so the mass will just be 500
500, yeah.
kilograms.
Yeah.
Seems like it, but it is a big room, 10 by 10 by 5. Anyway.
But,
yeah.
if it's the room, it's where of what?
Huh?
It's the mass of what?
The air in the room.
Okay.
Yeah. Delta Q is mc delta theta, which is 500, 1012, 10. So that would be 5,000 times 1012. So, that's roughly, if I took this as 1,000, that would be roughly 5,000,000. So it's about roughly 5 million joules. You need 5 megajoules to heat this room up.
Like,
Yeah. What's wrong?
it's the room, like,
Like this room, yeah.
Bigger than this room.
Big, yeah, yeah.
The length is right.
Yeah, 10, yeah, well, no, that's not even 10 meters. It's much bigger than this room. It'd be more like D213 maybe or something.
Yes.
Yeah.
So what's your question?
500 feet?
I know. It seems like a lot,
Oh, yeah.
but it is 500 kilograms.
But is it everywhere in the room that there's air?
Yeah, it fills up the whole room. It's like gas in a balloon.
Oh.
What if we put like different objects and it moves?
Yeah, well, this question is an empty
I
room.
know.
Yeah, yeah. But of course, it would be different if you put objects in it. But then it becomes more complicated because the objects would have heat capacities as well, and they would heat up at a different rate than the room temperature.
So you have to
In the exam, they could put it again, maybe like one object, not the different.
No, 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 no. If this question was in the exam, it would be an empty room. Yeah. So we need 5 megajoules of energy to heat up this room to room temperature of 20 Celsius. Okay? So how long will this take? Well, the electric heater has a power of 3 kilowatts, which is 3,000 watts. So power equals work over time. So that means time is work over power, which is about 5 million over 3,000. So cancel, 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 cancel. So that would be 1,333, is it? Yeah. No. Yes? No. No. 1,666. 1,666.
0.6.
Yeah. So that's roughly 1,670 seconds. Let's make this into minutes. If you divide by 3,600, what do you get? About 30.5, about 30 minutes.
It's a second. You can do 60.
Oh, sorry. I was thinking hours. Yeah. How many hours?
27 minutes. 27,
Yeah.
8 minutes.
So about 28 minutes.
Yeah, that's a lot of time.
Yeah. Now, will it take 28 minutes? No, it'll take longer because, as you said, there'll be objects in the room and their temperature will need to increase. The wall will increase in temperature. Some cold air will get in and some of the heat will be lost. So, in fact, 28 minutes is the perfect condition. It will take longer than 28. If half the energy is wasted, then it will take an hour to heat up the room to room temperature. Yeah. Okay. Next question. A physics student is making a latte. He mixes 200 grams of hot milk at 27 Celsius to 50 grams of hot coffee at 80 Celsius. What's the finest temperature of his delicious, warm, steamy latte? Right, so let's have a look at this one. So what you've got here is you've got you've got your milk, you've got your coffee. This is at 80 Celsius and it is 50 grams, so 0.05 kilograms. And then you've got your milk, which is at 27. That's pretty cold milk, but whatever. 27 Celsius. And how much milk do we have? 0.200 kilograms. What's the heat capacity of water? 4,200.
And the milk?
And the milk is 2,800? 2,800.
2,850.
2,850. So what's going to happen here, yeah? Capacity of the milk. So what we do is we mix this one together with this one and to form a new mixture. So what is the temperature of this mixture? So this mixture will have milk and it will have coffee mixed together.
In the exam, and they will give us the table whole time.
Give you what?
The whole table.
What do you mean?
Capacity.
Oh yeah, they give you what you need. So which will gain energy and which will lose energy? So which is hotter? The coffee. So the coffee will lose energy. So I'll write coffee, and that will lose energy. What about the milk?
Gain.
That will
Again.
gain energy. So the milk, that will gain energy. Yeah. Let's say that the final temperature of the coffee mixture is X. We don't know what it is,
Yeah.
it's what we want. How much energy did the milk lose? Sorry, did the coffee lose? What's the formula? It's M. What's the M for coffee? Sorry, this is coffee and this is milk. What's the M for coffee? 0.05. The capacity, 4,200.
Yeah.
Although it's not really that, but we'll use it. What is it?
418.
No, I mean, it's not even that because that's for water and coffee's not water, but it
Yeah.
doesn't matter. Now, how much energy did what was the temperature decrease in the coffee? Well, previously it was at 80
Yeah.
and later it'll be at X.
X.
Imagine X is a smaller number than 80. How much did it lose? It lost 80 minus X. Now, how much energy did the milk gain? Well, by the same reason, it'll be M, which is 0.2, capacity, 2850. Now, what is the temperature change for the milk?
27 plus X.
X minus 27.
X minus 27, because the milk got hotter.
Bam.
So imagine that the milk was at 30 Celsius, the drink was at 30. How much did the milk change by? 3.
The milk
The milk is
will
gonna be
increase.
hotter.
Yep.
So it will increase.
The milk will increase and the coffee will decrease.
But
So the X of
the
coffee.
plus should be.
No,
So Steven,
well, this is positive. Both these numbers are
No,
positive.
I'm not saying that.
No, first listen. Both these numbers are positive. Okay, now go.
I'm just saying if the 27,
Yep.
because it will gain
Yes.
the temperature.
Yes.
So the X will add into 27.
No. Listen. The milk is at 27 at the beginning.
Yeah.
It's at 30 at the end. How much did it gain? It didn't gain 30, it gained 3. 30 minus 27. X
Well,
minus
you know the
27.
temperature is 30.
Yes, exactly. So we know the temperature is X.
so the X of milk is.
I just
bigger
used
than-
30 as an example to explain it. The final temperature is X.
The X of milk is bigger than 27, isn't it?
Yeah, exactly.
At the end.
At the end,
Yes. This temperature at the end will be somewhere in between 27 and 80.
Mhm.
The milk will get hotter and the coffee will get colder.
Alright.
Yeah? Now, the energy
Oh.
of the coffee went into the milk.
Okay.
So in other words, the energy that the coffee lost should equal the energy the milk got. In other words, the energy just transferred from one material into the other material.
Okay.
So what you can say is these are equal. So you have 0.05 times 4,200 times 80 minus X equals 0.2 times 2850 times X minus 27.
What about if they don't have energy before,
Wait, give me a real question. What's your question?
like it's already on 27, so it would have some energy, right?
Yep.
So
And they both have energy at the start.
yeah, but they are different.
Yes.
Even if you transfer some amount, they won't be equal.
What? What are you asking me? Give me a clear question.
I'm just saying.
No, I don't want opinions, thoughts, or
I'm not-
ideas. I just want a question with a question mark at the end. So it's just our with teacher, question, go.
How this could be the same if you transfer some amount.
The temperature is the same at the end.
And
What do you mean how? If you mix milk and coffee,
Yeah,
and you're drinking it,
yeah.
do you drink like this? Oh, this milk is so cold, I just can't wait till I get to the hot coffee at the bottom. You know the temperature's the same when it's mixed up.
Oh,
Yeah, yeah. So, I mean, I only drew it as two layers at the end, but they're mixed up. Yeah. Now look, what type of equation is that at the end?
Quadratic,
Not
linear.
linear.
Linear. I'm not going to solve it. It's
Why?
because you know how to solve a linear equation.
Oh, I think we do.
Do you want me? Don't want me to solve this, do you? Like, what do you do?
Of course I know, Steven.
You multiply this in, don't you? You multiply this in, and then you take this. The x's to the left,
I know.
and the numbers to the right. You learned this in middle school.
Like 5 years,
Yeah.
6 years.
So I'm not going to finish this, but you put it in and you solve it and you get the x.
Next is,
Okay.
Yeah.
I mean, the hard part is getting this equation.
Of course, yes.
Once you have the equation, it's just basic maths then.
What's
Yeah.
1.3
The math teacher.
Well,
degrees?
what is it?
What's 1.3 degrees?
41.3. Thanks, KJ. Right. So the last one is the lead bullet hits the wall.
Lead bullet?
Lead bullet. Eaten lead. So here is the lead bullet. It is a mass of 0.01 kilograms, and it's moving at 100 meters per second. It hits the wall and it stopped moving. The kinetic energy was converted into heat.
Heat.
Let's work out how much hotter the bullet is. So first we need the kinetic energy, a half mv squared. This is converted into heat, delta Q. 0.005 multiplied by 10000. So 1, 2, 3, 4. 1, 2, 3, 4. So delta Q is 500. But what's the formula for delta Q? MC. What's the capacity for lead? It was like 138, was it?
Yes.
Delta theta. Something like 138, wasn't it?
let
129. So if you do 500 divided by 0.01 times 129, what do you get here? What you get?
387.59.
387.59 Celsius. That is how much hotter the bullet is. This bullet is nearly 400 degrees hotter.
Very hot.
I don't understand. Why did you bring that down?
Here, I'm solving for delta theta.
Basic equation.
No, that looks like 2.
That one is a Q. That one there's a theta.
Yeah,
Q.
that looks like a 2.
Whatever. Right.
One more.
Wait.
Yeah. Thanks.
Yes.
That 500, is it equals to or plus?
What 500? Equals.
500 equals that.
Yeah. The kinetic energy
Equals.
was converted into delta Q, heat energy.
I guess.
You get it?
Yes.
Well then that means everybody gets it. Right, there are the questions.
Should I